Hi everyone. Today I am going to tell you about a novel AI model called PreGAN that stands for Preemptive Migration Prediction Generative Adversarial Network, built for proactive fault tolerance in edge computing environments. I am Shresh Thuli, a PhD student at Imperial College London, and this is a joint work with Giuliano Casale and Nick Jennings. So we all know that in the recent years, the computational paradigms have shifted from cloud backends to edge devices. And edge computing follows the data gravity principle. That is, it moves the computational devices close to the end users, giving rise to a multitude of benefits. First, it offers low response times, possibly in milliseconds, crucial for time-critical applications. Second, it solves the data explosion problem. For instance, in smart cities, where terabytes of data are generated every hour, and transferring them to the cloud is either infeasible or may require expensive networking elements for high bandwidth processing. Third, it offers a closed-knit data sharing network that gives rise to increased data integrity, credibility, and security. Now, with edge computing becoming ubiquitous, it is essential to ensure that the edge nodes themselves do not become a point of failure for the running applications. And robust countermeasures are in place to incorporate overloads or failures in edge network or processing nodes. In particular, modern application demands of low latency task execution and resource constraints of edge devices exacerbate the problem of effective resource management at the edge. The increasing volumes of the data requiring immediate processing and the resource constraints at the edge are pushing the compute resources to their limits, giving rise to a high chance of resource contention and node downtimes. This leads to resource unavailability and violations of the service level objectives, or SLOs, that can possibly lead to significant financial losses. Further, the problem of developing a robust fault tolerance framework requires us to proactively predict faults before they occur and diagnose the root cause issues to be able to run appropriate remediation steps. For such systems to be within the strict specifications of modern industrial demands, they need to be able to resolve diverse kinds of system or network related faults. This may entail establishing the type of fault at the time of its prediction for a more informed recovery decision. Furthermore, to avoid overlooking any fault that may cause significant adverse effects later, and to avoid overhead of false positive predictions, such prediction models need to be extremely accurate. So in this work, we target a standard heterogeneous edge computing environment where all nodes are in the same local area network or LAN. Here, tasks are container instances generated from the sensors and actuators in the Internet of Things or IoT layer and communicated to the compute nodes via gateway devices. The edge broker takes all scheduling, management, and preemptive migration decisions in our system. We consider system contention type faults of resource utilization metrics such as CPU, RAM, disk, and network bandwidth. And to proactively prevent fault in a future interval of the system, we take preemptive container migration decisions over the active tasks in the system. Finally, we formulate our problem as a discrete time control setting where we periodically take preemptive migration decisions, say every 5 minutes, to avoid faults in a future system state. We call these time periods as scheduling intervals in the rest of the presentation. Let me now give you an overview of the Pregain model. At the start of each scheduling interval, our model takes two inputs. The first input is S, which is a scheduling decision for the incoming and active tasks in the system. The second input is W, which is a sliding window of the states of the edge computing environment, characterized by the resource utilization characteristics of the edge devices in the environment. In our model, we consider a state-of-the-art underpinning scheduler that generates the scheduling decisions S at each interval. Now, similar to a traditional generative adversarial network or GAN, our Pregain model has a generator and a discriminator network. It also has a fault prototype encoder that takes in the time series window of system states and predicts a fault class, that is, contention of the form of CPU, RAM, or network. The fault class then is sent to the generator that generates preemptive migration decisions in the form of a matrix with one hot vectors corresponding to the migration decision for each active task in the system. This migration decision is used to update the input scheduling decision and generate a new decision N, and both S and N are sent to the discriminator network. The job of the discriminator is to differentiate between the original schedule S and the new schedule N and give a likelihood score for each decision denoted by D. The one with the higher likelihood score is then used as the final decision for incoming and active tasks in the system. This architecture allows Pregain to be modular and utilize any underlying scheduler, for instance one that aims to minimize energy versus another that aims to minimize response time. Pregain just aims to modify that decision based on default class predictions and uses the best one. Further details on the implementation of each component, that is the generator, discriminator, or encoder as neural networks, can be seen in the paper. Let me now introduce the idea of coupled simulation that we leverage in this work, which is also referred to as co-simulation in literature. A co-simulator, akin to a digital twin, simulates an input resource management decision and generates estimates of quality of service or QoS scores to feed back to the decision model. A typical co-simulation loop works in 5 steps. First, we monitor a real system to generate characteristics such as resource utilization metrics of the hosts that characterize the state of the edge computing environment. Second, we send the monitored metrics to a decision model, which in this case is Pregain, that generates sample scheduling decisions to choose from. Third, we send the system state with the sample decisions to test to an event-driven simulator that quickly generates QoS estimates for each decision. 4, we send the QoS estimates as a feedback to tune the decision model and perform online optimization of the decision. 5, we enact the best decision of the decision model in the physical setup and continue this iteratively in a discrete time control setting. I shall now discuss how we train the Pregain model. As discussed before, the encoder network was used to predict the type of fault in the system, such as CPU, RAM, or network contention. To do this, we use a clustering-like approach where the true cluster class was determined by an industry-grade contention detection tool in Linux. The predicted class vector by the encoder network was then aimed to belong to this true fault class. A TSNE plot of a set of randomly sampled system faults predicted by the Pregain model is shown here. To train the GAN model, we use a slightly unconventional training style. We use co-simulated QoS scores to train the GAN model in a supervised fashion. So at the start of any scheduling interval, we run Pregain and execute simulations of the two decisions S and N to generate corresponding QoS score estimates. We then generate a one-hot vector corresponding to the decision with the higher QoS score and use it to train the discriminator network of Pregain. To test the efficacy of Pregain model, we ran our experiments on a cluster of 16 heterogeneous Raspberry Pi devices. For our workloads, we use the popular AI-based DFOG application benchmarking suite. These include object detection and natural language processing like tasks, all based on AI. We compare the Pregain model with baselines across several metrics. For fault detection, we use accuracy and F1 scores. For fault diagnosis, that is prediction of the specific host where fault has occurred, we use diagnosis metrics of hit rate and normalized discounted cumulative gain. Also, we measure the time it takes to run the fault tolerance approach relative to the time to take a scheduling decision and call this the overhead ratio. We also measure the improvement ratio, that is the ratio of intervals where the new decision N was better than the decision from the underlying scheduler, that is S, in terms of QoS score. Finally, we also compare the QoS metrics such as energy consumption, average response time, fraction of SLO violation rates, and so on. These results compare the detection, diagnosis, and fault classification performance of Pregain with 4 state-of-the-art methods. The confusion matrix shows the fault classification performance, whereas the table shows the detection and diagnosis performance. Clearly, the Pregain method has the highest detection and diagnosis scores with the maximum improvement ratio. with lower overheads compared to the baseline with the best detection scores, that is CMODLB. Here are some results that show the average energy consumption, response time, CPU, and RAM utilization in case of using Pregain model, which all are lower than when we use any baseline method. These are some additional results showing that the task allocation time, number of migrations, etc. are lower for the Pregain model, facilitating improved quality of service. Further, the fraction of violations of the service level objectives is also lower for the proposed method. For a more in-depth analysis and discussion of the results, I refer you to our paper. So to summarize, we present PreGAN, which is a GAN-style model that predicts fault class and preemptive migration decisions periodically for an edge computing environment. The high detection and classification accuracies of PreGAN facilitate efficient fault recovery for optimal quality of service. Specifically, PreGAN achieves an improvement of 8% in terms of energy consumption, 5% in terms of response times, and 12% in terms of SLO violations. It is also able to correctly identify faults, giving higher classification and diagnosis accuracies than the state-of-the-art models. PreGAN is able to achieve this with 24% lower overheads compared to the baseline method with the highest F1 score. This makes PreGAN an ideal choice for reliable edge computing with time-critical applications. As part of future work, we propose to extend PreGAN to utilize unsupervised models to work in settings without label data. Thank you for your kind attention. All our code and datasets are available on GitHub under BST license. For any questions, please feel free to email me on s.tully20@imperial.ac.uk.